So with new discoveries, the design codes will also be revised. Now, let's look at the original form for the UBC in UBC 1985. First of all, conceptually, you know that when we consider a structure like this, when we say that there's earthquake, the earthquake is usually denoted by ground motion. So ground motion means there will be acceleration measured horizontally like this. Now, before we stay with this definition, you should keep in mind that earthquakes do not give us an idealized loading like this one. When we consider a building like this, a three-dimensional building, because everything is three-dimensional, right? And you define the coordinates, which is at the center. You can define x, y, z at the center. Correct? That's a three-dimensional coordinate system. If you use Cartesian, the right-hand rule with this to be x and this to be y. Oh, I'm sorry, I need to write in a much bigger form so you can see it. X, y, z. Is that better? Okay. Now, the building is a three-dimensional, as well as the structure itself, as well as the ground. So if you consider the ground point, you can also define three-dimensional coordinates like this. So this point is, you can call it the ground level, just call it point O. So the point O is here, is at the base of the structure, and this is on the surface of the ground. Now, if you consider the motion of this point, in theory, how can this point O move? We know that the point O can move horizontally along the x-axis, also along the y-axis, right? So the consideration we have here, by considering that earthquake is modeled as a horizontal ground motion, is only true if you consider the displacements along the x or y axis. That being said, if you define the x to be here, z is the vertical direction, which is here, and the y will be the direction going into the bore, and that's y direction, because x is this direction here, this is x, and this is z. The positive y direction following the right-hand rule would suggest the direction pointing into the bore. So by this consideration and use it to model the earthquake loading, that means we only consider the horizontal ones. What about the, can ground move vertically? And the answer, of course, is yes, right? And for those of you experiencing, who had experienced earthquakes in the past, you notice that the earthquake doesn't just move horizontally, sometimes it will move vertically. So that means it is possible that the displacement can also be in the vertical direction. Therefore, in theory, you should also consider the vertical if you want to come up with a seismic analysis with improved fidelity. You need to consider the earthquake loading, not just horizontal, but also vertical. Because if you consider vertically, then the effect of axial force becomes crucial. Why it becomes crucial? It's because when you start moving objects going up, the actual loading along the axial direction, the actual axial loading may exceed the buckling load of columns. So when you consider earthquakes in the vertical directions, structures, especially building columns, can actually buckle because of excessive vertical acceleration. Now, horizontally, that also regards what we call the geometric effects. And just think about this. Think about this eraser. It has different dimensions on its plane. It has more slender, or let's say much longer dimension in the vertical axis, and horizontally it has a shorter dimension. What that means is this. Suppose I have an earthquake. I want to move this object going in this direction, along this direction. That means the ground is the board, and this is the building. So suppose you place this building on this. There are two different kinds of motion. One is going vertically, the other is going horizontally, right? So can anyone tell me that suppose this is a building, have two different cases. Case one, this kind of horizontal, well, what do you call it, ground motion, to this eraser is going vertically, right? Or going horizontally. Which one is more devastating to this building? Is going case one or case two? Which one?
Case two.
Who said case two?
Case
What's that?
Case one.
All right, Chris, and any other voices? Case one or case two?
Case one.
Some says case one.
I think case one.
One and case two. Okay, unfortunately, I don't know how to take votes. And so what's the answer? The answer is case two. Case two is more devastating to this structure. And the reason is because the strong axis for this building is the vertical axis. So if you load it like this, the effective, the same moment, the same overturning moment, let's say that assuming that the same overturning moment, it is more difficult to turn this building in this direction. But it's relatively easier to turn this building if you shake like this. Just imagine this kind of overturning. Can you see that? If the horizontal movement is like this, earthquake moves like this, it's more likely the building could actually fall in this direction. But it's not easy for the building to fall in this direction. You can find a slender object like this. You try to think about this. If you move vertically, this axis is the strong axis because it has a longer dimension compared to this dimension. So the shorter dimension is usually corresponds to what we call the weak axis of this plane. Therefore, when you consider this, you can choose to model this building either on this side or on this side, correct? Because we are only dealing with a two-dimensional structure analysis here, correct? That's the formulation. And that's how we're going to show you the procedure to calculate what we call the equivalent base shear. So when we do that, you can either choose to model it like this or model it like this. Which one you should use? So let's make this bigger here so we see it even clearer. One is the building will look like this, and the other is the building will look like this. I said case one, so this is case one. This will be case two. Wait a minute. Case one goes this way, actually. It's the other way around. So this is case two and case one. Now, is that clear to you that why case two is more devastating? Is that clear now? Case one is this. So that means it shakes horizontally like this. That means it goes like this. Case two is like this. So this is case two. Case two is like this. So when case two moves, the same moment, it has shorter distance. So it's going to produce a greater force acting or transmitting to the columns of this building. Suppose they are buildings. Which is why this is more critical. We don't have to worry about this one because it moves along its strong axis. But this one, in case 2, the building moves along its weak axis. So you have to consider this effect. Now, so this is one important discussion before you choose which side of the building to study. So that's one. Identify the weak axis and consider the worst case scenario. Now, with this, should you be happy? No, you shouldn't. Why? Because in reality, do you think that earthquake will just load your structure or attack your structure to say that, all right, the first 10 seconds, I'm going to load it only in the X direction. And the next 10 seconds, I'm going to load it to the Y direction. Do you think earthquake will do that? No, right? So what will earthquakes do? Well, earthquake will never tell you that when it's going to be simplified, it's only one direction or two direction. It's usually the